I'm so incredibly excited to take you on a little journey today into the hidden chemistry, really the invisible science behind the objects we interact with every single day. We look around and we mostly just see finished, complete items, right? But here's the crazy truth. Almost everything you're touching, seeing, or even drinking right this second is a mixture. So today we're going to learn how to decode these mixtures and, more importantly, how human ingenuity pulls them apart. Let's just pause and think about this for a second. How exactly do we get pure, sweet, white crystals of sugar from those tall, green, super fibrous sugarcane plants? Or think about the medical field. How in the world can doctors detect a disease like malaria using just one tiny, single drop of blood? Well, nature's default state is to mix things together. It's kind of what it does. But human science, that's the ultimate solution for taking those complex natural blends and separating them into the pure essential components that we literally need to survive and thrive. Okay, so here's our roadmap for today's explainer. We'll start with homogeneous versus heterogeneous mixtures. Then we'll hit the math of concentration, followed by the science of solubility. After that, we'll look at separation by crystallization, and finally, we'll wrap up with the art of distillation. First up, section 1, homogeneous versus heterogeneous, classifying our world. Just notice the stark visual contrast between these two beakers. On the left, we've got a homogeneous mixture. Think of a solution like sugar dissolved in water. It has a completely uniform composition. I mean, if you take a sip from the top or a sip from the bottom, it's going to be equally sweet, right? The solute, the sugar, and the solvent, the water, are perfectly blended. But then, look at the beaker on the right. This is a heterogeneous mixture, kind of like sand stirred into water. It is definitely not uniform. You can easily see those heavy sand particles, and if you wait a bit, gravity just pulls them right down to settle at the bottom of the glass. But sometimes our eyes can totally deceive us. What if a mixture actually looks perfectly blended, like milk mixed with water? Well, scientists use this brilliant little trick, the laser light experiment. If you shine a laser pointer through a true homogeneous solution, the beam just passes through completely invisibly because the dissolved particles are way too microscopic to hit. But if you shine that exact same laser through a mixture that has slightly larger suspended particles, like milk drops or maybe chalk powder in water, the light scatters. This scattering literally exposes the hidden particles floating in suspension, proving without a doubt that it's actually a heterogeneous mixture. Let's move on to section 2, the math of concentration, formulas that save lives. So our first formula here is mass by mass percentage. Basically, it tells us exactly how many grams of a solute are present in 100 grams of the total solution. And guess what? You use this all the time without even realizing it. Just look at this milk powder nutrition label. When a manufacturer tells you that there are 49 grams of sugar or 15.5 grams of protein in 100 grams of the powder, they are directly using mass by mass concentration. It's literally the standard way to guarantee the exact composition of packaged foods and spice mixtures. Now, what if you're working purely with liquids? Honestly, it's just much easier to measure liquids by volume than by weighing them out, and that brings us to volume by volume percentage. If you wander into your pantry right now and grab a bottle of white vinegar, you'll probably see a label that reads 5% V by V acetic acid. All that really means is for every 100 milliliters of that liquid, exactly 5 milliliters is pure acetic acid, and the rest is just water. It's that precise, exact concentration that makes vinegar the perfect, absolutely safe preservative for your food. And then we've got the hybrid, mass by volume percentage. Guys, this is where the math literally saves lives. In hospitals, doctors use intravenous infusions, like the 5% glucose strip you're seeing here. That means there are exactly 5 grams of solid glucose dissolved into 100 milliliters of solution. Or think about the oral rehydration solution, the ORS, formulated by the Indian pediatrician Dilip Mahalanobis. By mixing a highly specific mass of salt and sugar into a fixed volume of water, this precise mixture has saved literally millions of lives from severe dehydration. You really cannot just guess the amounts here. The concentration has to be spot on. Okay, so these 3 formulas, which you can see summarized right here in this table, are really the pillars of preparing solutions. And the so what factor here? It's absolutely massive. Just picture a farmer spraying pesticides on a rice crop. They use volume by volume percentage to mix the chemical with water. If they use the wrong formula and the concentration is too low, well, the crops get destroyed by pests. But what if the concentration is too high? They could ruin the entire harvest, poison the soil, and completely devastate the environment. Getting the right proportion is absolutely crucial. All right, section 3, the science of solubility, packing in the solute. Solubility is, simply put, the secret behind how much of a substance we can force into a solvent. You see, every solvent has a maximum capacity at any given temperature. When it hits that absolute limit, we call it a saturated solution, meaning it cannot absorb even one more tiny speck of solute. But here's the real magic trick. Temperature totally changes the rules. If you want to dissolve more of a solid, like sugar or salt, you just heat the liquid up. Heating it increases the liquid's ability to pack in solid solutes. Interestingly enough, it's the exact opposite for gases. If you heat a liquid, it actually loses its ability to hold dissolved gases. This whole rule about heating liquids to pack in more solids, it perfectly sets up our very first super incredible separation technique. Which brings us to Section 4, Separation by Crystallization, Nature's Purifier. Let's just walk through this incredibly satisfying lab procedure. So say we have some impure copper sulfate. First, we heat up some water and add the copper sulfate until the hot water is completely saturated, like packed to the brim with the compound. Second, while it's still piping hot, we filter it to get rid of any undissolvable dirt or impurities. Now comes the amazing part, step 3. We let that clear, hot liquid cool down very slowly. Remember our solubility rule from a minute ago? Cold liquid can't hold as much solid as hot liquid, so as the temperature drops, the excess copper sulfate gets literally forced out of the solution. But it doesn't just fall out as random mush. It arranges itself into these brilliant, pure blue geometric crystals. Finally, step 4, we just filter those pure crystals right out. And honestly, this brilliantly illustrates that crystallization isn't just some lab trick. It is nature's ultimate purifier. Coastal communities in India have used variations of this exact method for centuries, boiling concentrated sea brines to produce pure Panganga and Karkach salt crystals. And if you want to see this process scaled up by nature over millions of years, you just have to look at the massive, absolutely breathtaking natural quartz crystal formations found deep inside places like the Masmai Cave in Meghalaya. It is the exact same scientific principle at work, just on a grander scale. And finally, Section 5, the art of distillation, pulling liquids apart. Now, distillation takes advantage of the simple fact that different liquids boil at different temperatures. By heating a mixture, the liquid with the lower boiling point turns into vapor first. We then capture that vapor, cool it down in a condenser, and turn it back into a pure liquid, leaving the other liquid completely behind. Now, basic distillation works great if the boiling points of the two liquids are more than 25 degrees Celsius apart. But what if they're closer than 25 degrees? That's when we bring in a powerhouse technique called fractional distillation. This is the exact process used in massive industrial refineries to take raw, crude petroleum straight from the earth and carefully pull it apart into everyday things like petrol, diesel, and liquid petroleum gas. From the lab scientists extracting and purifying the sugar we started our journey with, all the way back to ancient artisans, these separation techniques really represent our mastery over the natural world. Get this. In Kannauj, India, they still use an ancient distillation setup known as the Deg Babka method. They actually distill the scent of the earth right after the first rain, capturing it into a highly sought-after natural perfume called Midi Ka Ittar. Human ingenuity truly is amazing. It transforms nature's complex, chaotic mixtures into the pure, essential substances that literally define our daily lives. So, as we wrap up this explainer, I want to leave you with a little challenge. Take a look around the room you're sitting in right now. Apply what you've learned today and look at it through the lens of a chemist. What unseparated, hidden mixtures are sitting right there in front of you? Is it the milk in your coffee, the metal alloys inside your electronics, or hey, even the very air you're breathing? The world is a beautifully complex mixture, and now you know exactly how the science of separation decodes the whole shebang. Thanks so much for watching, and keep exploring.